In this lecture, as well as the next two lectures, we're going to determine the derivatives of the basic functions of higher mathematics, namely the exponential, logarithm, hyperbolic, and trigonometric functions. We start with the exponential function, f of x equals e to the x. Recall that the graph of every exponential type of function, g of x equals a to the x, with a positive, passes through the point 0, 1. In other words, has y-axis intercept 1. The number e was defined as that number for which the slope of the graph of the corresponding exponential function at this y-axis intercept is exactly 1. We will continue to take the existence of such a number as an article of faith because we want to use the exponential and log functions as early as possible in our course. We will return to this assumption when we have the tools to rigorously establish the existence of e. However, we can take the time to make the assumption a bit more plausible. Remember that to compute the derivative of g of x equals a to the x at x equals 0, we would write down the difference quotient for the point 0 a to the 0, which is 0, 1, and the nearby point h a to the h. That difference quotient has the form a to the h minus 1 all divided by h. And then we take the limit as h tends to 0 of that difference quotient. Determining this limit is difficult, so we delay it and instead use some numerical work to justify our assumption that a number e exists for which the limit is 1. We do this by choosing a equal 3 and looking at values of the difference quotient for successively smaller values of h. And we see that the value of the difference quotient is consistently larger than 1, so it is plausible that the limit is greater than or equal to 1. We do the same thing for a equal 2.5, and we see that the value of the difference quotient is then consistently less than 1. So it is plausible that for a equal 2.5, the limit is less than or equal to 1. The next assumption is more of a stretch. We assume that there is some sort of intermediate value theorem for these limits. That is, since the limit of the difference quotient is less than 1 for a equal 2.5, and bigger than 1 for a equal 3, there ought to be a number e between 2.5 and 3 for which the limit is 1. For now we take this on faith, and we make a promise to nail it down at a later date. So we now take as a fundamental assumption that the derivative of the function e to the x at x equals 0, which is the limit as h goes to 0 of e to the h minus 1, all divided by h, that limit is 1. It turns out that we can then compute the derivative of this exponential function at any point. This nice result will follow from the property of the exponential function that e to the power p plus q is the product e to the p times e to the q. To compute the derivative of e to the x at a point, we form the difference quotient as usual. That's e to the power x plus h minus e to the power x, all divided by h. And you can factor e to the x out of this using the property we just mentioned, and write this as the product of e to the x with the quotient e to the h minus 1 over h. Then we take the limit, and the constant e to the x factors out. Remember that we're taking a limit as h goes to 0 and x is fixed. So you get that the derivative of the function e to the x is e to the x times its limit e to the h minus 1 over h, which is exactly the derivative at x equals 0, which is assumed to be 1. So we have the somewhat surprising result that for f of x equals e to the x, f prime of x is exactly f of x. In terms of the graph of e to the x, this says that the slope of the tangent line at the point x e to the x on the graph is always exactly the same as the y-coordinate e to the x. This has very important implications for the growth of the function e to the x. Namely, the larger that e to the x becomes, the steeper is the slope of his tangent line, i.e., the more rapidly it grows larger. This is the first hint of the staggering growth rate of the exponential function. Differentiating the general exponential function leads to a limit we can't evaluate yet, but we will work around that. Here's the direct calculation. The derivative of a to the power x is, of course, the limit as h goes to 0 of the difference quotient, a to the power x plus h minus a to the power x, all divided by h. And a to the x again factors out using our properties of exponentials, and we're left with the derivative of a to the power x is exactly a to the x times the derivative of a to the x at x equals 0. So the general exponential function has the same property as the exponential function e to the x, only with a constant of proportionality, which is just the derivative of a to the x at x equals 0. We can determine the constant numerically, as we did earlier, for a equal 2.5 and a equal 3, or we can look at things again and use the observation that the natural logarithm and the exponential function are inverses, which can be written, the log of e to the b is b, and the exponential of log b is also b. So you can write a to the x as e to the natural log of a to the x. But the natural logarithm has the property, in fact every logarithm has the property, that the log of a to the x is just x log a. So a to the x is e to the x log a. Then you can differentiate using the chain rule. The derivative of a to the x is the derivative of e to the power x log a. And we know what that is. That's the derivative of the exponential function, which is just e to the x log a again, times the derivative of what's inside the exponential function, which is x log a. And the derivative of x log a is just log a. So you end up with the fact that the derivative of a to the x is a to the x times the natural logarithm of a, which is a bit simpler in appearance than our earlier result that the derivative was a to the x times the derivative at 0. Of course, it follows that the two are equal. Rather than memorize the formula for the derivative of a to the x, I would recommend that you just remember the properties of log and exponential, and that they give us a to the x equals e to the power x log a, and proceed from there. With the help of our rules for differentiation, especially the chain rule, we can now differentiate complicated functions involving powers, roots, and exponentials. As an example, consider f of x equals e to the power 3x squared. We have f prime of x equals the derivative of the exponential, which is just the exponential again. So we start off with e to the 3x squared, and then by the chain rule, we have to differentiate what's inside the exponential function, 3x squared. And so we end up with 6x times e to the 3x squared. The tangent line to the graph of this function at the point 1e cubed, that's x equals 1, y equals e to the 3x squared equals e cubed, has slope 6e cubed, which is 120.5 roughly. So the equation of the tangent line is y minus e cubed divided by x minus 1 equals 6e cubed. That slope is extremely big. If you don't believe it, just try sketching a line with slope 120.5. What that means is that at this point on its graph, this function is increasing at a very dramatic rate. Another example. Let g of x be the square root of e to the x minus x cubed. Then remembering that the derivative of the square root function x to the 1/2 is 1/2 x to the minus 1/2, we can write g prime of x equals 1/2 e to the x minus x cubed to the minus 1/2, and then we go inside and differentiate e to the x minus 3x squared. The slope of the tangent line to the graph of this function at the point x equals minus 1, y equals roughly square root 1 over e plus 1, which is about 1.17. The slope is minus 1.125, So the equation of the tangent line at this point is approximately y minus 1.17 divided by x plus 1 equals minus 1.125. Since the tangent has negative slope, we can conclude that the function is mildly decreasing at this point. Finally, an example which requires a bit more work. Consider h of x equals the exponential of e to the x squared. That's e to the power x squared. Well, you just walk through with the chain rule. H prime of x is e to the x squared. Differentiating the exponential just gives it back. Then you go inside and differentiate e to the power x squared. Well, that just gives you back e to the x squared times the derivative of x squared, which is 2x. Rest assured, we will look at even more complicated examples as we go along. Now we turn to the natural log function, which is the inverse of the exponential. It turns out that the fact that the inverse of a function and the function undo one another allows us to find the derivative of the inverse when we know the formula for the derivative of the original function. That long mouthful of words is easily summarized in mathematical notation, knowing that f inverse of f of x is identically equal to x, true for all x for which the left-hand side can be computed, implies that we can differentiate both sides of this identity. So we write down this identity for the exponential and the natural logarithm and then differentiate the identity making use of the chain rule. We start with e to the power log x is just x, identically. We differentiate both sides to get e to the power log x times the derivative of log x is identically 1. Notice that we use the chain rule again on the left side. Now we can solve for the derivative of log x equals 1 over e to the log x, but that's just 1 over x. So that's our formula for differentiating the natural log function. The derivative of log x is 1 over x. Notice that this means that the slope of the tangent line is very close to 0 for extremely large positive values of x. For example, if x is 10,000, the slope of the tangent line is 10 to the minus 4th, which is practically horizontal, which means the function is increasing, but very, very slowly. So now we can use the chain rule to state very general formulas for differentiating expressions involving exponentials and natural logarithm functions. We know that e to the power f of x has the derivative e to the power f of x times f prime. And we know that any function of e to the x, when differentiated, has the derivative f prime of e to the x times e to the x. Both of these formulas come directly from the chain rule. With the logarithm function, we have similar formulas. The derivative of log f of x is 1 over f times f prime, usually written f prime over f. And the derivative of any function of log x is f prime of log x times 1 over x. Some examples. The derivative of e to the power fraction x divided by x squared plus 2x plus 3. Well, you differentiate the exponential and you just get it back and you write it down. Then you have to go inside the exponential and differentiate the quotient. And you get, by the quotient rule, in the denominator the square of x squared plus 2x plus 3. And in the numerator, the derivative of the denominator minus the numerator times the derivative of the denominator. And you can just leave it like that. There's no point in cleaning it up unless we're going to use it for something else. Another example, the derivative of the square root of e to the 3x plus x squared plus 2 is 1/2, that same expression to the minus 1/2, times the derivative of that expression, the one inside the square root. The derivative of that expression, again using the chain rule on the exponential, is 3e to the 3x plus 2x. Another example, the derivative of the logarithm of the quantity e to the x plus 4. You can write it down immediately. You differentiate the log by taking the reciprocal of what's inside, and then by the chain rule you multiply by the derivative of what's inside. So you get 1 over e to the x plus 4 times e to the x plus 0. And you don't bother writing down plus 0, of course. The derivative of the log of e to the x squared plus 4 is almost the same. You write down the reciprocal, 1 over e to the x squared plus 4, taking care of differentiation of the logarithm, and then by the chain rule, multiply by the derivative of what's inside the log, which is 2x e to the x squared plus 0. Another example, the derivative of the square root of 4x plus the log of x squared plus 2. Well, the square root is easy. You bring down the 1/2 and take the log of x squared plus 2 plus 4x to the minus 1/2. Now you must multiply by the derivative of what is inside the square root function. The derivative of the first term inside, the log of x squared plus 2, is 2x over x squared plus 2. And the derivative of the 4x is 4. And you're done. Be sure to take the time to understand each of these examples. They contain a sizable number of techniques you're going to need for survival on exams. To differentiate a to the x for a general exponential base a, I find it easier to take logarithms and then differentiate the resulting expression rather than memorize the formula. So you write f of x equals a to the x and take logs to get the log of f of x is x log a. Now differentiate both sides of this identity to get f prime over f equals log a. Then you solve for f prime. The derivative of a to the x is f prime at x, and that's log a times f of x, namely log a times a to the x. You can use this same idea to find the derivative of h of x equals log base a of x. If h of x is log base a of x, that means that a to the power h of x is identically equal to x. Now take natural logs of this identity to get h of x natural log of a equals natural log of x. Now we differentiate this last identity and solve for h prime. You get log of a times h prime of x equals 1 over x, and therefore the derivative of log base a of x, h prime of x, is equal to 1 over x times 1 over log a. I wouldn't even consider memorizing this expression. A test question would be more likely to ask you to derive it than to regurgitate it. Using this trick of taking logarithms and then differentiating allows us to differentiate some otherwise intractable expressions. For example, consider g of x equals x squared plus 4 to the power 3x. You can't use the power rule on this because the power is not a fixed number, it's variable. So you take logs, and you get the log of g of x equals 3x times the log of x squared plus 4. And both sides of this identity are very easy to differentiate. The left-hand side, the derivative is g prime over g. The right-hand side, you use the product rule. You get 3 times the log of x squared plus 4 plus 1 over x squared plus 4 times 3x times 2x, using the chain rule and the rest of the product rule. And so you clean it up, multiplying through by g of x, of course, and you get g prime at x equals the enormous long expression 3 times the log of x squared plus 4 plus the fraction 6x squared over x squared plus 4. That whole expression times x squared plus 4 to the power of 3x.